Believe it or not, what you just saw was a chicken being thrown inside an aircraft engine. This shocking video shows one of the many tests aircraft engines must undergo before they're used on an aircraft. Well, throwing chicken inside an engine might sound shocking. Wait until you see what 900 gallons of water can do to an engine. But why are these tests important? According to the Federal Aviation Administration, over 10,000 bird strikes occur each year, averaging more than 26 hits in a day. Each year, bird strikes cause an estimated $2 billion worth of damage to flying aircraft, with the majority of incidents inflicting destruction of the engines. If you remember the miracle on the Hudson, then you might be more familiar with bird strikes than you think. But a flock of birds hit this plane. It ended up destroying both of the engines. This is just how much damage a bird strike can cause. To prevent birds from destroying the engines, manufacturers have figured out a way to test the engines against such strikes. One invention used in this test is the chicken gun, which is a large diameter compressed air cannon that fires chicken corpses at the plane, including its engine. This invention simulates a high-speed bird strike and is used to see whether the engine is capable of withstanding such a strike. Most modern aircraft engines are capable of simply ingesting the bird and continuing to rotate as if nothing happened. But if a strike is broken, a blade or something bigger, it can result in an engine shutdown. Because engines are so well engineered and built, bird strikes rarely cause fatalities. Well, except to the bird. However, it's been shown that a bird strike can still take down a plane. Because of that, this test is possibly one of the most important ones an aircraft engine needs to go through. Each day, aircraft engines are exposed to extreme weather conditions, and oftentimes they're forced to operate through rain and storms. The exposure to water in the skies means that each engine has to be able to function properly during such conditions. They need to be able to take in large amounts of water, so to test engines for how capable they are, water ingestion tests are a must. Manufacturers do these tests by forcing a stream of water into running engines. They fire up to 900 gallons of water per minute into the engine. When this test is conducted, the goal is to have the water pass through the engine and be shot out the back without reducing thrust. If the test is a success, it means that the engine can handle the forecast rainstorms and run through pools of water. Alongside this test, the engines are also put through a wind test. Crosswinds can make the aircraft lose its direction, making it almost impossible to land or take off. Freezing temperatures can be a huge problem for an engine, especially if the engine isn't tested against these conditions. One of the ways this concern is tested is by placing the engine in an environment where the temperatures are cold, allowing the engine to spend days or weeks there and testing how it operates in that temperature. Another way to test the engine against ice is by shooting ice into a running engine. These big balls of hard compacted ice are set to mimic the effects of flying through a hailstorm. This way, manufacturers can determine whether the engine will be damaged from the ice or whether it's able to ingest the ice and continue operating. When the weather is colder and the temperatures get lower, we have icy conditions that can further damage the engine and cause a terrible accident. These conditions are particularly tricky and require different types of ice particles to test the engine. Huge balls of ice are thrown into the engine to know if it can withstand them and how quickly it can recover without a lot of damage done. Many people wonder what the average price of an engine in a commercial aircraft is. Engines are definitely the most expensive component in any aircraft. The average price of an engine that powers a Boeing 737 is around $15 million. The Rolls-Royce Trent engine, one of two engines for the Boeing 787 jetliner, costs about $20 million at list price. The GE90, which powers the Boeing 777, has a list price of $30 million. General Electric, or more specifically, GE Aviation, produces engines available on the Airbus 300, 310, 330, and 330neo, large turbofan engines that power some of the largest airliners, including Airbus of 350 and Airbus of 380, are much larger and more complex. With high power requirements, such engines can cost between $35 and $45 million. Rolls-Royce is a renowned British company that has been manufacturing jet engines for over 100 years. Their engines are widely used in both civilian and military aircraft, and they are known for their reliability, efficiency, and performance. The manufacturing process of Rolls-Royce jet engines involves several intricate steps. The manufacturing process involves precision casting techniques, such as investment casting, to create complex components with high accuracy and minimal waste. Components like turbine blades and vanes are cast using these methods. The individual components are then carefully assembled into sub-assemblies, such as the combustion chamber, compressor stages, and turbines. After successful testing, the sub-assemblies are brought together for final engine assembly. This includes fitting the engine's core components together and integrating accessories like fuel systems, electrical systems, and control mechanisms. Not only do they use this chicken gun for testing engines, but they also use it to fire birds on the windshield to make sure it's safe and strong enough to withstand birds smacking into it. Today, manufacturers have figured out lots of ways to make sure bird strikes don't cause major damage. The most important part of the engine is the blades that rotate at high speeds up to 4,000 revolutions per minute, causing the engine to reach full thrust and power so it can lift the airplane off the ground and into the sky. Of course, these blades need to be securely placed into the engine, making sure each one is secure. But what happens if a blade comes out? Well, this is where all the tests come into play. Blade-off testing is an air safety test that has one mission in life, and that's to make sure that each blade stays firmly attached in the engine and doesn't have any chance of coming out while the airplane is flying. A blade that comes loose or flies out is one thing that should never happen to an aircraft engine, but since it has previously happened to some engines in the past, they know how to make sure the engine is secure before they even attach it to the airplane. Going at around 4,000 revolutions per minute and having a blade come off could cause so much damage, much more than a bird strike for sure. The blade could come out and hit other moving parts of the engine, causing enormous damage, potentially flying through the aircraft fuselage, causing safety of flight damage to the aircraft, or potentially causing fatal injuries to the passengers on board. So these tests are focused on checking the blades are well fixed in and can't fly out. And in case one would come out, the detached blade or blades shouldn't cause huge damage to the engine, and also ensure that the engine will be fully able to function without the blade or blades. In this testing process, a small explosive is attached at the base of one of the blades. As soon as they run the engine, they detonate the explosive to know if the blade will stay inside the engine chamber. If a blade comes out during this testing, then they go back to the drawing board and redesign how to better secure the blades into the engine. And then do all the testing again. One small blade the size of your finger can cause huge damage to the engine and the fuselage, and possibly could lead to an unwanted accident or an emergency landing.
Commercial plane engine manufacturing is a complex and sophisticated process that involves multiple stages, from research and development to final testing and installation. It is carried out by highly skilled engineers, scientists, and technicians in state-of-the-art facilities to design, produce, and validate the engines that power modern commercial aircraft. The process begins with extensive research and development efforts. Engineers and scientists conduct in-depth studies to understand the aerodynamic, thermal, and mechanical requirements of the engine. They use advanced computer-aided design software to create detailed models of the engine, conducting simulations and calculations to optimize its performance, efficiency, and reliability. They also explore innovative materials, technologies, and systems that can enhance the engine's performance, reduce emissions, and improve environmental sustainability. The selection of high-quality materials is critical to the performance and durability of the engine. Advanced alloys, composites, and lightweight materials are carefully chosen for their strength, heat resistance, and weight-saving properties. These materials are then processed through various techniques, such as machining, forging, casting, and forming, to create the various components of the engine, such as the fan, compressor, combustor, turbine, and exhaust nozzle. Advanced manufacturing techniques are employed to produce engine components with exceptional precision. Computer-controlled machines, such as computer numerical control machines, are used for high-precision shaping and forming. Specialized processes, such as 3D printing, may also be used to create complex components. Strict quality control measures are followed to ensure the components meet the required specifications. Once all the components are manufactured, they are carefully assembled to create the complete engine. Skilled technicians use specialized tools and techniques to align and connect the various components. This process requires meticulous attention to detail to ensure that the engine is assembled correctly and functions as intended. Strict quality control checks are conducted throughout the assembly process to ensure that the engine meets all performance requirements. After assembly, the completed engine undergoes extensive testing to validate its performance and safety. The engine is run at various power levels and operating conditions to simulate real-world flight scenarios and ensure it meets the required performance specifications. Environmental testing, including extreme temperature, vibration, and pressure tests, is also conducted to ensure the engine's durability in harsh conditions. Non-destructive testing methods, such as X-ray inspection and ultrasonic testing, are used to detect any defects or flaws in the engine components. Once the engine successfully passes all the tests and inspections, it undergoes a final inspection to ensure it meets all the quality standards and regulatory requirements. This includes checking for proper alignment, tightness of fasteners, and correct installation of all components. Any necessary adjustments or corrections are made at this stage to ensure the engine is in perfect condition before proceeding to installation. Upon passing all the validation tests and inspections, the engine is ready for installation on an aircraft. The engine is transported to the aircraft manufacturer, where it is carefully integrated into the airframe, connected to the fuel and electrical systems, and thoroughly tested once again to ensure it is functioning properly and ready for flight. Before an engine can be used in commercial aircraft, it must undergo certification by aviation regulatory authorities, such as the Federal Aviation Administration in the United States or the European Union Aviation Safety Agency in Europe. Certification involves rigorous testing and evaluation of the engine's performance, safety, and compliance with applicable regulations and standards. The manufacturing process of Rolls-Royce engines involves a series of advanced and intricate processes carried out by highly skilled engineers, technicians, and craftsmen. The engines are produced with meticulous attention to detail and undergo stringent quality control checks at every stage to ensure their performance, reliability, and safety. At Rolls-Royce factories, various manufacturing techniques are utilized, including precision machining, forging, casting, and forming. Computer-controlled machines, such as CNC machines, are used for high-precision shaping and forming of engine components. Advanced technologies, such as 3D printing, may also be employed to create complex parts. Rolls-Royce manufactures a wide range of aircraft engines for different applications, including civil aviation, military aviation, and marine propulsion. Some of the notable engines produced by Rolls-Royce include the Trent series, which powers popular commercial aircraft such as the Airbus A330, A350, and Boeing 777, the RB211, which has been used on various aircraft models, including the Boeing 747 and the Lockheed L-1011 TriStar, and the Adur, which is used in military aircraft such as the Hawk and the Seppicat Jaguar. Rolls-Royce is also at the forefront of developing advanced engine technologies such as hybrid electric and sustainable aviation solutions aimed at reducing emissions and improving environmental sustainability in aviation. In addition to engine manufacturing, Rolls-Royce also has facilities for engine testing, maintenance, repair, and overhaul services to ensure the continued performance and reliability of their engines throughout their operational lifespan. With its global manufacturing footprint, cutting-edge technologies, and innovative engine designs, Rolls-Royce is a world-leading manufacturer of aircraft engines, powering aircraft across the globe and contributing to the advancement of aviation technology. The GE9X icing test is a critical evaluation conducted by General Electric to ensure the performance and safety of the GE9X aircraft engine in icy conditions. During this test, the engine is exposed to simulated icing conditions in a controlled environment to assess its ability to operate effectively and safely in such challenging conditions. The test involves spraying ice particles onto the engine to simulate the icing encountered during flight, and the engine's performance, efficiency, and ice-shedding capabilities are thoroughly evaluated. The GE9X icing test is an important step in the engine certification process, ensuring that the engine can operate reliably in all weather conditions, including icing conditions, to meet the stringent requirements of aviation safety regulations. Swiss Airlines, a leading airline in Switzerland, relies on turbojet engines to power its fleet of aircraft. The production process for these engines typically involves several key stages, including design and development, engine component manufacturing, assembly, testing and quality assurance, and delivery and installation. The design and development phase entails close collaboration between Swiss Airlines and renowned engine manufacturers such as Rolls-Royce, Pratt & Whitney, or General Electric. Engineers from both parties work closely to design and develop turbojet engines that meet the specific requirements of Swiss Airlines' aircraft fleet. Factors such as performance, efficiency, emissions, and maintenance requirements are carefully considered during this stage. Once the engine design is finalized, the engine components are manufactured using precision machining, forging, casting, and other advanced manufacturing processes. High-quality materials, including alloys, composites, and lightweight materials, are used to ensure durability, performance, and reliability of the engine components. The engine components are then meticulously assembled according to the engine manufacturer's specifications. Highly skilled technicians and engineers carry out the assembly, ensuring that each component is precisely fitted and interconnected to create a fully functional turbojet engine. Strict quality control procedures are followed at every step of the assembly process. After the engine is assembled, it undergoes extensive testing and quality assurance checks. Bench testing is conducted, where the engine is operated under controlled conditions to assess its performance and emissions. Endurance testing is also carried out to evaluate the engine's durability and reliability over an extended period. The engine must pass all the necessary tests and quality checks to ensure compliance with aviation standards and regulations. Once the turbojet engine successfully completes testing and quality assurance, it is delivered to Swiss Airlines for installation on their aircraft. Highly trained maintenance teams carefully install the engines on the aircraft, following strict procedures and guidelines to ensure proper integration and functionality. Throughout the operational lifespan of the turbojet engines, Swiss Airlines conducts regular maintenance and overhauls to ensure optimal performance and reliability. Routine inspections, repairs, and component replacements are carried out as needed, in compliance with the engine manufacturer's recommendations and aviation regulations. The production of turbojet engines for Swiss Airlines involves a complex and sophisticated process, requiring the collaboration of skilled engineers, technicians, and manufacturers. This ensures the delivery of high-performance and reliable engines that meet the stringent requirements of the aviation industry. The assembly of the Rolls-Royce Trent turbojet engine takes place at various state-of-the-art manufacturing facilities around the world. Rolls-Royce has manufacturing sites in countries such as the United Kingdom, Germany, and Singapore, where different components of the engine are produced and assembled to create the final product. The journey of creating a Trent turbojet engine begins with the design and engineering phase. Rolls-Royce's team of skilled engineers and technicians work meticulously to design and optimize every aspect of the engine, from its aerodynamics to its materials, to achieve the best possible performance. Advanced computer simulations and cutting-edge manufacturing techniques are employed to ensure that the engine meets the highest standards of efficiency, durability, and safety. Once the design is finalized, the manufacturing process begins. The components of the Trent engine are produced using advanced manufacturing methods, such as computer numerical control machining and additive manufacturing, which allows for precise and complex parts to be produced with high accuracy. Rolls-Royce also employs advanced materials, such as lightweight alloys and composites, to reduce the engine's weight and increase its efficiency. One of the key components of the Trent turbojet engine is the fan, which is responsible for producing the majority of the engine's thrust. The fan is made up of numerous blades that are carefully manufactured to precise tolerances to ensure smooth and efficient airflow. The fan blades are typically made from lightweight materials, such as titanium or composites, to reduce weight while maintaining strength and durability. After the individual components are manufactured, they are carefully inspected and tested to ensure they meet Rolls-Royce's strict quality standards. This includes rigorous testing of each component's performance, durability, and safety under extreme conditions, such as high temperatures and pressures. Any components that do not meet the required specifications are either repaired or replaced to ensure that only the highest quality components are used in the final engine assembly. Once all the components are deemed suitable for assembly, they are brought together at Rolls-Royce's engine assembly facilities.